All right, welcome to our class this morning. We are, as I look at the calendar, so we're going to have our test between the 22nd and the 25th. So know that that will be happening. Tomorrow you still have reproductive system quiz 12 to do. A week from tomorrow will be your lab practical. On the 28th, I'll need everything turned in by the 30th at the latest. So all your assignments, everything, and some people have not been doing their quizzes like they're supposed to, and that's not a good thing. I have graded everything. My laptop crapped out last night, and I about died because my laptop is my life, so that I'm not stuck at home forever. And I fixed it this morning.
Don't like that.
Yay. So I'm happy to, but anyway, so I had to get on my stupid desktop computer at home and grade everything, but everything, all the quizzes have been graded now. Homework, we're still getting those put in, but there are some of you who have not been turning in your homework, and you got to get that in, because you can take a look at your grade now and go, oh crap, I need to be doing that. So make sure you stay up on everything. We can't all fall to pieces in the last few days of the semester. Okay.
Just a heads up, quiz 7 still isn't in there.
Okay, so here's the thing with quiz 7. It became quiz 8. So there's no quiz 7.
Okay.
Yeah. So
start moving everything. Okay.
Yeah. So just, in fact, it should be gone, but if it's still showing up.
No, it's gone, but I was like writing things in on my.
Oh yeah, no, it's done. It's out of there. So no quiz 7. Yep. Because that would have been, for you guys, it would have been the digestion quiz. But then for online, it was already quiz 8. So I just went, screw it. This is what we're doing. So everything's in that needs to be in right now. Okay. So there it is. Stay on top of life and we'll be good. So today, if you just popped in, you weren't here a little bit ago, grab your packet, your glomerular, there you go, your glomerular filtration packet. We didn't have as good an understanding when we did our physiology quiz as I had hoped. So I wanted to make sure. I can't go into it because some of you have not taken it and therefore we can't go over it, but I will go over this to make sure, because I know which things to highlight without, you know, giving anything away to those of you who have not taken it yet. Okay.
And then, Ms. G, one more question for the test 4. Is that being rounded or anything, or the score we get is?
I don't know.
Okay. I just didn't know whether to throw it in to add up my points or not.
Just throw it in like that, and then anything else will be exciting.
I'll take it. Perfect.
But
Thank you.
just throw it in like it is right now. Yeah.
Okay. Sounds good. Thanks.
You really, I mean, you can put it on, you know, if you're keeping track of it, but if you go into the grade and you scroll to the bottom, it tells you exactly where you're at. So.
I know.
Okay. All right. So there's that. Okay. So I believe what I want to do today, you know what, let's go through the packet. You know, that really lasers everything down to where I need you to know, and then I can make sure that you know stuff, and then we'll go back through the lecture notes and make sure we understand anything. Did you guys find the key to the ABGs? Okay. So that's there if you want to check your answers, and we'll save the last 15 minutes or so to go over any ABG questions that you might happen to have. Okay, so we had jump on this and go fast. Not so fast, but go right away. Okay, so so remember the functions of the kidney. Well, actually, let's go to I don't know where that is. Okay. But if we take a look at the kidney, remember that we're going to obviously filter the blood, get rid of nitrogenous waste. We're going to maintain fluid balance, maintain electrolyte balance. We're going to maintain acid-base balance. We're going to have long-term maintenance of blood pressure and the stimulation of red blood cell production. I gotta make sure I'm recording. Red blood cell production by erythropoietin. So those are all the things that the kidney is going to do. And remember, there are 3 processes that the kidney does to achieve this: filtration, reabsorption, and secretion. Okay. Remember, with filtration, you're going to go from capillary to tubule. So from the glomerulus to the glomerular capsule. Then reabsorption, you're going to go from the tubule to the capillaries. So you're going to go proximal convoluted tubule primarily, but loop of Henle and distal convoluted tubule and collecting duct. There will be some reabsorption through all of those places, but remember, primarily proximal convoluted tubule into the peritubular capillaries, and then secretion will be from the peritubular capillaries back into the tubule at any point in the tubule. We can have that happen. But primarily proximal convoluted tubule, distal convoluted tubule, where we're going to be maintaining sodium balance, hydrogen balance, that kind of thing. All right. So in order to achieve filtration, so I'm just going down through the list, through the packet right now. Okay. All right. So what force drives filtration of the glomerulus is hydrostatic pressure. So the force, and I'm not going to go into big detail because you already know what hydrostatic pressure is. Okay, so hydrostatic pressure, pressure of the blood in the glomerulus, is going to push the material out into the capsule. And then glomerular filtration is bulk flow. So anything smaller than the holes. Remember that there are fenestrated capillaries and filtration slits in the podocytes of the visceral border of the Bowman's capsule or the glomerular capsule. And so it's through the fenestrations and through the filtration slits that you're eventually going to get the material into the capsule. And so whatever is smaller than the holes is going to go through. It doesn't matter. And if there's enough pressure due to hydrostatic pressure to get the stuff out, then it's going to move. So what's going to be in your filtrate? Water, ions, nitrogenous waste, organic molecules. Everything smaller than the hole. What don't you want to come through? You do not want proteins, and you do not want blood cells to come through. That would indicate most likely inflammation or damage to the filtration membrane from one sort or another, primarily too high blood pressure, chronic hypertension. Remember that the filtrate is isotonic to the plasma of the blood, to the interstitial fluid of the cortex. Everything's 300 milliosmoles. So you're just pushing stuff out, and then stuff will get reabsorbed, but to the same concentration as what's in the blood. Okay, blood pressure in the glomerulus is about 60 millimeters. You know what? Let's do this again. I don't know why I'm making you look at me. That's lame. Not anymore. Okay, so go away from looking at that. Okay. All right. So let's remember, I'm going to go forwards now instead of backwards, just because it'll be easier to type it in on here. Okay, so remember, the ultimate contributor to filtration of the blood is going to be systemic blood pressure. And whoops. And we want a systemic blood pressure of 120 over 80 millimeters of mercury. Okay, so if I have a systemic blood pressure of 120 over 80, that is going to give me my afferent arterial. Afferent arterial BP will be 60 millimeters of mercury. And why is it higher than what we typically see in other arterioles leading into capillary beds? It's short and large diameter. Okay, so that's going to deliver a lot of blood into the glomerulus. So if it's delivering a lot of blood into the glomerulus, then you're going to get, oops, you're going to get glomerular hydrostatic pressure, which we abbreviate HP, and then, you know, subscript G, but that works. Oh, that works. Okay. Of 60 millimeters, milliliters of mercury. Okay. So then when we have that, then we get, I'm going to have to come over here, net filtration pressure, which is the pressure that drives filtration. Because remember, you have opposing forces, and we'll just go ahead and do that right now. So net filtration pressure of 17 millimeters of mercury. But I can give you, on the exam, I can give you just some numbers, and then you'll have to be able to do it. So I'm going to go ahead and do the equation right now for net filtration pressure. So net filtration pressure equals HPG minus the sum of HPC plus, which is the hydrostatic pressure of the capsule, and hydrostatic pressure, osmotic pressure of the glomerulus. Okay, so under normal circumstances, if HPG is 60, typically hydrostatic pressure of the capsule is 15, and osmotic pressure of the glomerulus is 28, and then that would give you this combined total of 43, which then would give you a 17 millimeter of mercury net filtration pressure. Okay, and then net filtration pressure is going to determine, ultimately what we want is our glomerular filtration rate. Sorry, or GFR of 125 milliliters per minute. Okay, all right, so please, oh, those shouldn't be backwards. Oh, dang it, wrong kind of arrows. So you know what I mean. They should just be going one direction. They shouldn't have, I don't care. Okay, so just know that they're gonna, well, I don't know, we could go the other way. We could say glomerular filtration rate is due to a 17 millimeter net filtration pressure. Anyway, okay, but you get the idea. All right, so so please know those relationships. Okay, so if that is, in fact, I'll just save that because I'll post it. Okay, yes, it's there. Okay, so okay, so then we go to number 5. What two pressures oppose filtration and what are their values? So capsular hydrostatic pressure, 15 millimeters of mercury. Glomerular osmotic pressure, 28. Normal net filtration pressure, 17. With a glomerular filtration rate, 125 milliliters per minute, how much plasma would be filtered? That's 180 liters in 24 hours. Okay, so remember, if our GFR is going to be too high, then we're going to have a lot of sodium chloride in the filtrate at the macula densa, and we're going to slow it down. Okay, so we're going to vasoconstrict. Oh, Eleni, I'll get into those controls in just a minute. Hey, if our GFR is too low, that means not enough flow is going past it. Maybe we're like 90 millimeters of mercury, milliliters per minute. And so not enough material is being filtered. So our chemoreceptors are not going to be as stimulated. So they were overstimulated in too high of a GFR. They're understimulated in too low of a GFR. And so we're going to have to adjust to that in whatever ways that we need to. Okay, so remember that we have two mechanisms that we want to kick in. In fact, I'm going to go to the, actually, let's go to our notes. I'm going to go to the PowerPoint right now and pop through that, and then we'll get caught up to where we are. Okay, so just remember where your kidneys are, retroperitoneal, okay, One's higher than the other, right's lower than the left, whatever. Okay, so remember you've got a cortex on the outside part. That's where all the filtration is going to be. So that's where all the afferent and efferent arterioles, and then our peritubular capillaries, all of that is going to be in the cortex. And then in the medulla will be the renal pyramids, so these triangular structures. Okay, so the renal columns that are carrying the blood vessels in from the hilum are going to cut through the pyramid, and in doing so, they're going to create the triangles of the medulla. At the ends of the triangles, they're papillae, and we'll talk about those in a minute. So collecting ducts, that's what make these lines all in the renal pyramids, are the collecting ducts that are taking care of all of the nephrons. Okay, so the glomerulus, remember that's the ball of capillaries. The capsule is what surrounds it. Proximal convoluted tubule is going to come right off the glomerulus. I don't know for whatever reason, but it was pretty straightforward in the quiz to show you proximal convoluted tubule as the answer, and most of you put distal convoluted tubule. So I have no idea what you guys were looking at. Distal would be after the loop of Henle. So the glomerulus is the start, glomerular capsule, and then the tubule coming off of that is proximal convoluted tubule. You're going to have a loop of Henle going down, coming back up again, and then proximal or distal convoluted tubule, and then collecting duct. Make sure you know what kind of epithelium is there and why. So cuboidal epithelium, mitochondria, microvilli, so you can do lots of active transports. You can, because remember, you've got to do the active transport of the sodium into the interstitium before you can bring anything else in from the lumen, including water, sodium, all of the solutes. Remember, you have a thin descending limb, thick ascending limb, and then distal convoluted tubule. Be mindful of the arrows. Be mindful of the size of the tubule so that you know which side you're talking about. Okay, I don't know, just make sure you know all of those things. All right. The only biggest difference between cortical nephrons and juxtamedullary nephrons is this long loop of Henle. So these are the nephrons that are really going to dilute your urine so that you can dip way down here, remember, and so that we can get to 1200 milliosmoles out in the interstitial fluid. And so vasa recta is going to be on the long loops of Henle, and then notice we do still have peritubular capillaries, but just not loops of, not like vasa recta, because we're not really going down into the medulla. So we really wouldn't be changing the osmotic gradient. It's going to stay 300 up here. Okay, so we need to regulate GFR. So if we take a look at who's going to be involved in that, remember the juxtaglomerular cells are going to be around the afferent arteriole. Okay, so they're mechanoreceptors. They're detecting the stretch that's there in the afferent arteriole to help with the myogenic mechanism, which we'll look at in just a minute. The JG cells are responsible for secreting renin in times of low blood pressure. So remember that low blood pressure will always secrete renin. So here are the podocytes, those yellow things. So they're wrapped around the capillaries, creating those filtration slits, and then there'll be the fenestrations then in the actual capillary walls. So there's the juxtaglomerular cells around the afferent arteriole. Always, you've got blood in, blood out. So this is afferent, this is efferent. Afferent's bigger around than efferent. Here is the thick ascending limb as it becomes the distal convoluted tubule. Have these chemoreceptors right here. Almost misspoke. So chemoreceptors, remember, macula densa cells are chemoreceptors to detect the sodium chloride concentration after we've done almost all the reabsorption that we're going to, because we're going to do 65% in the proximal convoluted tubule, 25% in the loop of Henle, and then 3 to 5% in the distal convoluted tubule, and 1 to 2% in the collecting duct. So we have reabsorbed just about everything, and so that's why we're taking a look at and see, is it what we want it to be? If we take a look at this, you can actually see the fenestrations in the capillary wall. So all these dotted lines show the fact that there are little openings, pores in the capillary wall, and then pores in the between the podocytes, the filtration slits, the podocytes. Okay, that just shows it some more. So we got that. All right, remember filtration membrane has to be thin. So we're going to have, now let's go to this picture. Okay, so we have the simple squamous epithelium or endothelium of the capillary of the glomerulus and the fenestrations in here. Then we have the basement membrane, the shared basement membrane between the foot processes of the podocytes. So these little fingery things that are interdigitating to create the filtration slits. Okay, so this is where I wanted to get to. So we got that. Filtrate is everything in the plasma except proteins and cells. Urine is metabolic waste and unneeded substances because we grabbed everything back, or we grabbed everything back. All right, so we need to make sure, here we go, that we control glomerular filtration rate. Okay, so NFP, so we have that, and then that's good. Okay, so this is where I want to be. So now we're taking a look at question 9 in the pack, well, question 8 in the packet. So it says, in an exercising individual, the afferent arteriole will constrict to avoid excess fluid loss. Okay, so what's happening is that our pressure is high. So the very first thing that we're going to do when we are in any kind of situation, I don't care if it's high blood pressure, low blood pressure, this is what's going to kick in first, is our myogenic mechanism. Okay, so if it's high, if we have high stretch, so high blood pressure on the arterial walls of the afferent arteriole, then we're going to vasoconstrict. Okay, and we can vasoconstrict in 2 ways. One, we will either just that inherent property of vascular smooth muscle is that it contracts when stretched, or this right here, we can release a vasoconstrictor. Now this is for vasodilation, but we can release a vasoconstrictor also from the macula densa when our blood pressure is too high. So remember, high blood pressure, vasoconstriction at the nephron. But if our blood pressure is low, then we want to relax our vascular smooth muscle here. So we'll inhibit contraction of the vascular smooth muscle. We'll vasodilate the afferent arteriole. So these are what's listed is low blood pressure. Okay. All right. So then I also added in 8, low systemic blood pressure causes vasodilation of the afferent arteriole. So we call these two together, this intrinsic mechanism is autoregulation. So I just put that right there. Autoregulation. So autoregulation is what we do at the kidney, at the nephron, not even at the kidney, at each individual nephron, which is really awesome that we can take care of nephron by nephron the blood pressure. Okay, I like that. All right, then the second thing, so myogenic mechanism is the first thing that we're going to do. And the reason why that's the first thing that we're going to do, because it's at the beginning. It's as the blood is coming into the nephron, we're going to turn the dial at the beginning to get filtration where we want it to be. But then we check at the end and we look to see, is this concentration where we want it? And if it's not, we either speed it up or we slow it down. And so that's the second mechanism, that's tubuloglomerular mechanism. And so when we have low blood pressure, we have low filtrate floor osmolarity or osmolality. So there's not as much sodium chloride in there because we didn't filter as much. And so who picks that up? So the macula densa cells pick up that information, and then they cause a vasoreactive chemical for vasodilation now. So they'll stop secreting vasoconstrictor molecule, and we can actually secrete a vasodilator to increase if we need to make it even more. But we're going to stop the vasoconstriction for sure. Okay, so that's question number 10. High osmolarity or high sodium and chloride in the ascending limb of the loop of Henle, where the macula densa is, as it becomes the distal convoluted tubule, will cause afferent arterioles to constrict by releasing a vasoconstrictor, or with low flow, vasoconstrictor secretion is less. And then we're going to find that because the macula densa cells are in the juxtaglomerular apparatus, right here, we also have the JG cells in that juxtaglomerular apparatus. So if the macula densa is involved with low blood pressure situation, then look at what happens over here. Boom, the JG cells will will release renin right there, and then we've gone out to the rest of the body. Okay, so in the extrinsic mechanism, this affects, so this is nephron level. Nephron. Okay, extrinsic, this is systemic. So not just your kidneys are filtering like they should, your brain is also being affected by how much blood is getting there. And so you have to be careful. You want to do intrinsic first because you don't want to mess up the flow that's going to the rest of your body. But if you're in a low blood pressure situation, you better kick in an extrinsic mechanism because it could be a systemic cause. And so we want to make sure that we are doing something that will benefit not just the kidneys, but benefit the rest of the body. And so hopefully by now we know this renin angiotensin mechanism. So we'll go through the steps. So the JG cells, juxtaglomerular apparatus, will release renin. Renin will, see, we're catalyzing this right here, angiotensinogen. Ugh, they went too far. Angiotensinogen to angiotensin 1, and then angiotensin 1 into angiotensin 2, and in the lungs with the presence of angiotensin converting enzyme. And just by the way, in case I hadn't mentioned this before, or you hadn't heard it or something, it's angiotensin converting enzyme receptor number 2 is what COVID-19 is binding to. So it's interesting that, that's why it's in your lungs. That's why it's so bad, because we've got ACE in your lungs, and COVID-19 is hooking into that. And I posted something yesterday, I guess it was, on Facebook. I'm going to send you guys the article too, is what really makes us sick from COVID-19 is our genetics. And that's what I've maintained all along, because we get such a variety in symptoms, and how it can be so simple and almost asymptomatic in some people, and can be lethal and fatal in other people. What's the difference? Well, there's something about us that's not about it's not about the virus, it's about us. And if we could get to the bottom of that, anyway, I could talk for days about that. That's next semester in the immune system. Let me tell you, we'll be discussing, that'll be like, okay, COVID-19 and how your immune system works. And that'll be like our case study for the whole unit. All right, so we've got angiotensin 2 being produced then. So what is it going to do? Well, first of all, angiotensin 2 by itself, remember, is a vasoconstrictor. So it's going to go out to all of your arterioles. Systemic arterioles cause peripheral resistance, increased blood pressure, and increased GFR. But it can do it secondarily by stimulating the adrenal cortex to release aldosterone, which will go to the kidney tubules. Okay, now I know there's this little thing that says, oh yeah, aldosterone makes sodium get reabsorbed. Aldosterone, that's the second effect. That's what we want, but what is the mechanism? So I need you to know the mechanism too. Okay, so what is the mechanism of aldosterone? Is to increase the number of sodium potassium pumps in the basolateral membrane of the tubules of the distal convoluted tubule. So we're putting more sodium potassium pump, so we'll pump out more sodium into the interstitial fluid, which will allow more reabsorption of sodium, and then water follows salt. Water's not going to follow through the same channels. Water will follow its own channel, so you'll increase the osmolarity, so water will want to come in. But what if you need some more water than that? Then angiotensin II will also stimulate the release of ADH from the posterior pituitary, and it will also make you thirsty. So all of those ways, we are trying to raise blood pressure by increasing blood volume. All right, then, question number 11. So now I'm going back to the packet. In periods of extreme stress, the sympathetic nervous system will override autoregulation and increase sympathetic flow to the kidney, result in what two important effects? Okay, so we're going to get constriction of the blood vessels, shunting blood, the renal blood vessels, shunting blood away to reduce fluid loss. But then the other thing that we put in somewhere else in the packet, so I'm just going to put it in here. Oh, there it is, right there. Okay, so here is the stimulus of the JG cells on the kidney to produce renin. So we get intense vasoconstriction and we get renin release. Okay. All right. Okay, so does anybody have any questions on any of that? I really marked that up, but that's what I need you to know. So if you can know all the whys and the hows and whys and wherefores of this chart, you'll be fabulous. You'll be swimming in points. Okay, so let's go to what's in our notes. Okay, so we got all of that. All of that is in words. There it is. Boom, boom. So there's all that. Okay, so let's do tubular reabsorption. So now we're to the back of the first page, which is early filtrate processing. Okay, so where are we time-wise? Okay, we're okay. So water is no, don't read that. Okay, summarize reabsorption in the proximal tubule. So let's go to this. Well, let's go to this one first. No, because that doesn't tell us. Let's do this one. So this chart is super good, or this drawing is super good in showing us what's going on. So let's look at what's going on. All right. So the first thing, absolutely first thing we need to do is this right here. Okay, so we need to pump sodium into the interstitial fluid. Raising is osmolarity. That will then prompt or promote the reabsorption of water. And remember, know which ones are passive and which ones are active transports. Okay, so notice with the sodium, what are we always doing as we're pumping it out? We need to have a supply of potassium to pump against that gradient, and so we'll have these potassium channels right here as well, so that we're just recycling this potassium primarily. We will reabsorb some, but we really don't want to reabsorb sodium potassium, because remember, when we reabsorb sodium, we usually get rid of potassium because we can't have them both, because then that messes with our membrane potential and our heart arrhythmia. Okay, so we're going to pump the sodium out first, and then that allows sodium to just come in here passively, okay, because we've created a deficit of sodium in here. Okay, so there's not as much sodium inside as there was before, and because the sodium's wanting to come in, we're going to use the same co-transporter right here with the active transport of glucose, because how much do we want to reabsorb? All of it. Okay, so we're going to, by the end of the proximal convoluted tubule, we will have absorbed 100% of the glucose and amino acids, but how much of the filtrate? We'll absorb 65% of the total amount of filtrate. Okay, so that's by the end of the proximal convoluted tubule, 65% of the filtrate's being reabsorbed, but 100% of the glucose and amino acids. Okay, chloride's going to go passively, potassium, any fat-soluble substances, those will all just go passively as well. All right. Okay, so there's that. There, you can take a look at that. All right, loop of Henle. So we want to make sure we understand what's going on in the descending limb. We are reabsorbing through water through osmosis because the simple squamous cells of the thin descending loop are permeable to water but impermeable to solute. Then we turn around in the ascending limb, and then here's those sodium potassium 2 chloride channels. Oops, see right there, co-transporter. And so the ascending limb of the loop of Henle is permeable to solute because of the sodium potassium 2 chloride channels and impermeable to water. And then calcium and magnesium will just passively go to. Okay, and then what is the role of the loop of Henle? The purpose of the loop of Henle is to, this is just, we'll get back to that. We'll get back to that. Okay, so the purpose of the loop of Henle is to create a dilute, we'll look at right here, is to create a dilute urine, to get rid of more water than we normally would have if our fluid was isotonic, we wouldn't get rid of that much water. And so remember what we're doing on the thin descending limb. We're not secreting. Where water is being drawn out because of the increasing medullary osmotic gradient. There it is. Circle that. Okay, so remember, because, and that's going to be all the way through here and all the way over here and inside in the middle, everywhere. Everywhere is going to have this osmotic gradient that the loop of Henle is plugged into. So because this gets more concentrated, more water comes out, but then what does that do in here? It concentrates it inside of here. So then what's going to happen? Some of it's going to start to flow out, but then we can get to the thick ascending limb. Because we don't have as much as we used to, we want to pump out lots as much as we can. And as we pump out as much as we can with those sodium potassium 2 chloride channels, then that dilutes the urine. So it's 3 times less concentrated than it was before, three times more dilute. And because we're not going to do any more significant reabsorption from the distal convoluted tubule and the collecting duct, then it's going to stay 100 milliosmoles. And then by the time we get down here, that shouldn't be that dark a yellow. But anyway, by the time we should get down here, that's when we have the pale yellow urine. So how do we maintain our medullary osmotic gradient so that we can still nourish the cells that are all involved in here? Is by losing water and gaining sodium chloride on the descending limb of the vasorecta, and then the opposite events will happen on the ascending limb, and then you don't lose any osmotic gradient that way. Okay, so there we go. All right, so let's just look at what happens with ADH. Oh, first of all, I have to get rid of that. Oops. Okay. So, all right. So what happens in the presence of ADH? So this is normal on the left. Here's what happens when we have ADH present. So what are we doing in this case? Again, ADH is going to cause water reabsorption, but what is its effect? Is to increase the number of aquaporins or water channels, aquaporin, in the distal convoluted tubule and the collecting duct. Whoops. All right, and so what you can see, and that totally makes sense, that it would be isotonic to whatever you were outside of here by the time you got down to the same location, because it's just going to keep drawing water out and it's going to become very concentrated. Okay, so there's that. And so diuretics, and then here's this, and then I add a little bit. You can read through that, why we lose potassium in thiazides, why they're also K-wasting, if you want to read through that. Okay, we got all that. Boom. That's good. Okay, so if we finish looking at the packet, aldosterone is stimulated by an increase or decrease in what ions? Okay, so remember, aldosterone is going to be secreted for 2 reasons. One, if I have high plasma potassium or low plasma sodium. Okay, so high potassium, low sodium will cause aldosterone secretion. And then what does aldosterone do? Puts the pumps in the basolateral membrane, and then reabsorbs the sodium, pumps out the potassium. What does antidiuretic hormone increase in the luminal membrane? Water channels or aquaporins. So in times of dehydration, we'll both have high ADH and high aldosterone, so that we reabsorb and retain water. But in times of overhydration, we'll decrease ADH and decrease aldosterone. And then by the end of the medullary collecting duct, only 1% of the filtrate remains. Remember, we filtered 180 liters of fluid a day, and by the time we get to the end, we only produce 1.5 liters of urine a day. So that's it's a little less than 1%. Okay, let me just really quickly go through some important things about the water stuff, and then if you have any questions on ABGs, then we can take a look at that. All right, so we know fluids are reabsorbed from the GI tract, excess fluids and electrolytes in our kidneys, in our sweat, in our GI tract, whatever. The 6 functions of water we got. The amount of water depends on the amount of fat tissue. The more fat tissue you have, the less water you'll have. Newborns have the most because they're the most protein-like, and then the more body fat you have, the less protein you have. Remember the fluid compartments, intracellular and extracellular, but extracellular is divided into interstitial fluid and plasma. So intracellular 62, interstitial 30, and plasma 8% of fluid. And then ions, electrolytes, you know those. And proteins are the colloids, and non-electrolytes would be glucose. Remember that we need to equal the positive and negative charges in a fluid compartment. And then we know how we get and lose water. So food and drink and cellular metabolism, and then we lose it through our kidney, skin, lungs, and GI tract. We know what happens with osmosis, hypotonic and hypertonic. Okay, so let's go through the low homeostasis chart again. So we'll talk about the water disturbances, so the problems, and then what's happening. So in hypervolemia, what we did was we increased both osmolarity and volume. So we gave you an isotonic solution. So IV fluid, for example. So then the volume went up, but the osmolarity doesn't change. Hypovolemia, we lost both water and solute. So that would be a decrease in volume, but no change in osmolarity. Blood loss, vomiting, diarrhea, those things that are nutrient rich, solute rich. Overhydration would be too much just, straight water. So an increase in volume, but a decrease in osmolarity, drinking too much water. And then dehydration is also hypotonic loss of water. So this is a decrease in volume, but an increase in osmolarity because you lost just water and you didn't take the solute with you. Okay, fluid homeostasis, so we have ADH, thirst, aldosterone, and sympathetic stimulation. With ADH, remember ADH is produced by the hypothalamus. So where are we going to detect that we need ADH release? Because we can release ADH without angiotensin II. So the plasma osmoreceptors are the strongest stimulus for ADH release. And so if those osmoreceptors up in the hypothalamus start to crenate, because the interstitial fluid and then of course intracellular fluid is going to be lost, the cells will crenate, and then the hypothalamus will produce ADH, and then ADH is to put aquaporins in to increase water absorption from the filtrate. All right, so make sure you know these two relationships with ADH. Okay, so plasma volume with ADH, volume will go up and osmolarity will decrease because I'm reabsorbing water. But on the quiz, it asks for urine concentration, urine situation, and some of you didn't put that. And so urine volume will decrease and osmolarity will increase. That's what's going to make your urine look yellow. Okay. Dehydration leads to thirst, dry mouth, plasma osmoreceptors, and low blood volume and pressure. So then under any time that we have low blood pressure, we're going to release renin, and then enzyme converts angiotensin II. 1 to 2 is ACE, and then aldosterone release, vasoconstriction, the sodium potassium pumps again. And then when we get sympathetic stimulation, then we'll decrease or we'll increase afferent arterial constriction, which will result in less blood flow to the glomerulus and less urine loss. But the other thing that we need besides the vasoconstriction is the renin release. And that's the packet. All right, so you don't have a lot of time to do fluids, but here I think the fluids are probably okay because we kind of just did them now anyway. So we got a few minutes left. Does anybody have any questions or anything that they want me to do, ABGs or whatever?
The test is open tonight or after?
Nope, not till Wednesday.
Till Wednesday, okay.
It won't be open until Wednesday. And then it'll be open through Saturday, but it won't be open tonight. No, far from it.
My classes get mixed up. I think my math is open tonight through Thursday.
Yeah, no, ours will open on 22nd. Tomorrow we'll do embryology in lab, and then we will
we have the quiz tomorrow.
Kahoot. Yes, you have a quiz tomorrow. You have reproductive system quiz. Yeah, so get that baby done. And you should just get that done today so then you don't have to think about it anymore. Yeah, so that's it. I got nothing else. Okay, good. Then I will see you tomorrow at 9 o'clock and we'll learn about how babies are formed. Not how they get made, but how they, once they get made, then how do they grow into babies. So, all right, have a great rest of your day and I will see you tomorrow.